Well, last time we learned that all parallelograms are quadrilaterals, and then we learned some properties of parallelograms. For instance, opposite sides are congruent. Opposite angles are congruent. Consecutive or adjacent angles are supplementary. Can we go the other way? In other words, if opposite sides are congruent, can we be sure that we have a parallelogram? The answer is yes. It goes both ways. What about angles? If opposite angles are congruent, we know that if we have a parallelogram, then opposite angles are congruent. Now, if opposite angles are congruent, do we have a parallelogram? Yes. It goes both ways, for both angles and sides. And we learned another thing about parallelograms. If we draw in a diagonal and another one, they'll bisect each other. Well, if you have something, a quadrilateral, and you don't know if it's a parallelogram, if you can draw the diagonals and they bisect each other, then you do have a parallelogram. In other words, that goes both ways also. In a parallelogram, the diagonals bisect each other. Conversely, if the diagonals bisect each other, you have a parallelogram. Most everything we learned about parallelograms in the previous video goes the other direction. The only one we haven't found a converse for is supplementary angles. Everything else goes both ways. If opposite angles are congruent, it's a parallelogram. Opposite sides are congruent, it's a parallelogram. Diagonals bisect each other, it's a parallelogram. What about that first part? If the opposite sides are congruent, then we have a parallelogram. Well, that kind of a converse actually stems from a previous converse theorem we have. Well, what do we know? Oops. What do we know when we draw this diagonal here? What do we end up with? Remember, we did something like this to show that the lines were, to show that the sides were congruent. Now that we have that the sides are congruent, it's very easy to show that these two triangles we just created are congruent. After all, this side is congruent to this side is congruent to this side, and this side, what's congruent to itself. So we have that side, or theorem, which tells us these two triangles are congruent. Well, if they're congruent, then the angle opposite this side must be congruent to the angle opposite this side, which means that we'll say this is alpha, and this is alpha prime, and these two are congruent angles. But wait a minute. Back when we studied parallel lines and transversals, we had a theorem which said if we have two parallel lines cut by a transversal, the alternate interior angles are congruent. But we also had a converse theorem for that, which said that if we have two lines, which may or may not be parallel, cut by a transversal, if alternate interior angles are congruent, the two lines cut by the transversal must be parallel. So we can use our converse theorem that we had back when we were studying parallel lines to show another converse theorem, which is that we now have a parallelogram. At least this way we can show that these two are parallel. That's not quite a parallelogram because these have to be parallel also, but we can use exactly the same reasoning. After all, this side's congruent to this side, so this opposite angle here, say that's beta prime, is congruent to beta. And by exactly the same reasoning, these two lines cut by this transversal must be parallel because the alternate interior angles are congruent. The other converses are actually very easy to show also. And they're easy to use. So this video probably won't be that long, because I don't think you're going to have any trouble using the converse of all these theorems in order to solve problems. So why don't we just go ahead and start solving some problems here. Well, here we have a problem where the Dim brothers, my old friends, Inseam and Fleabite, they're doing some more geometry problems. And they get it all wrong, of course. They always do. What did they do wrong this time? They claim that two pairs of sides are congruent. Well, they came close. Opposite sides have to be congruent. Here we have adjacent sides that are congruent. And that's just borderline silly, because everybody knows by now it's the opposite sides that have to be congruent. If this were 7 and this were 5, we'd be in good shape with respect to this problem anyway. So that's the error. Consecutive sides don't count. You need two pairs of opposite sides to be congruent, and then you've got it. Or if you can show that one pair of opposite sides are congruent and parallel. See, if you've got two pairs of congruent sides, you don't have to show that anything's parallel. It follows. Boom, you got it. However, if you can only show that one pair of sides is congruent, then you need to show that they're parallel also. If you can do both of those, that means these two will have to be congruent and parallel. So either two pairs are congruent or one pair is congruent and parallel. This problem is kind of easy, but it's important because it explains a lot of things. You've seen those I forget what they call them, ergonomically designed keyboard platforms or something like that. They actually have some cool name that I don't remember. They sit on top of a desk, and you can set a laptop or keyboard on it, and the keyboard can be lowered down to the level of your desk where you can sit down. You can raise it a bit if you'd like to sit higher. You can actually stand up at your desk, and this platform will rise up. And the cool thing about it is the top part, which goes up and down, is always parallel to the floor. Well, they work exactly the same way this thing works. Why is it that this thing stays horizontal? Well, it's because this is going to be fixed to be horizontal. The dimensions we have here are that these two opposite sides are equal, and these two opposite sides are equal. So no matter how we can shift this down, skew it, in other words, so it turns out to look maybe more like that, really smashed down, right? It won't matter how far we smash this down. We could get it so that this line is right on top of this one. It won't matter. This will always be parallel to this one, and this side will always be parallel to this side also. But that's not the most important part. What's important is that if we fix this, so we just screw it in here somewhere, maybe in 2 screws, so that it has to stay horizontal. That means this top part can shift way off to the left, off to the right, but it will always be parallel because it doesn't change length. As long as these two opposite sides and these two opposite sides remain the same length, it doesn't matter how we shift this top top side here, left, right, so it goes up or down, and left and right, it's going to have to stay horizontal, that is to say, parallel to this piece right here. If you want to try it, I've done it. It's really easy to do with, say, popsicle sticks and those little push pins that you use for the cork boards. You can stick 4 popsicle sticks with the little push pins right there, and as you move the sticks around, you will see that they always stay parallel no matter how you move them around. And here we have a question about a quadrilateral, which we don't know too much about yet, but we know a couple of things. So I went ahead and drew it in here. We have our quadrilateral x, y, z, and x, y, and w, z are congruent and parallel. And we know from a previous theorem that congruent and parallel, remember, we can have 2 pairs of congruent sides or 1 pair of congruent and parallel sides. These two are congruent and parallel, so we have a parallelogram. So, what would be true here? See, angle y and angle w plus angle w equals 180. Well, adjacent angles, or consecutive angles, are supplementary. Opposite angles aren't. Opposite angles are congruent, but they could be any particular value, so we can't really say anything about what they would add up to. Well, it looks to me like A is the bad one. Let's double check the rest of them. How about angle x congruent to angle z? Well, in a parallelogram, opposite angles are congruent. Those are opposite angles, so that makes sense. Wx is congruent to zy. Well, these are opposite sides of a parallelogram. Yes, they must be congruent. Wx and zy are parallel. Again, they're opposite sides of a parallelogram, so they are parallel. That's the bogus answer there. By the way, if they had said angle y and angle z are supplementary, or angle y and angle x are supplementary, that would be true. The only thing y can't be supplementary to is the opposite angle. Well, in this problem, what they want you to do is construct a couple of lines that intersect each other and bisect each other, and then connect up the endpoints of these lines to form a quadrilateral, like they did over here. Now, the question is, I would say, is it a parallelogram? But they're saying it is a parallelogram. Why? Well, another one of those converse theorems that we have. Almost every theorem we have which tells you a fact about parallelograms can be used in the converse. And this is one of those. Remember, if we have a parallelogram and draw the 2 diagonals, they bisect each other. Now, we have a quadrilateral with diagonals that bisect each other, and it turns out it goes the other way too. If you have a quadrilateral with 2 diagonals that bisect each other, you must have a parallelogram. It goes both directions. That's really all you had to say in this, was that the fact that you have 2 diagonals which bisect each other means that from the converse theorem, you have to have a parallelogram. Yeah, here's one where they're getting kind of tricky. If they throw enough lines in, you'll probably get confused. I know I do. Let's try to figure out what it is they're asking us here. I went ahead and drew in part of this. BF and DE are congruent. That's this one and this one. And in fact, they're 12. I'll write that in later on. Congruence is the important thing right now, I think. And CF equals 8. That's this one here. And we'll get to that. But what we want to find is this one here. what is this? Well, if this was a parallelogram, we'd already know that they're equal. Or, in this case, congruent. Well, what can we do here? Well, let's see here. We've got a triangle over here and another triangle over here. Now, if we could show that this triangle formed by BF, FC, and BC, in other words BFC, and this triangle here, AED, if we could show that they were congruent, then this side corresponds to this side we know is congruent to this one. That leaves these two sides congruent, and we'll automatically know what this is. The question is, are these two triangles congruent? Well, let's find out. We know that these two sides are also congruent, by the way, because they said it was a parallelogram. That's the big quadrilateral here. So, these two sides are definitely congruent. And keep in mind, when laying out a problem like this, I frequently just insert what we know. And we may or may not use everything that we know. For instance, we might need to know that these two sides are congruent. We might not. Let's put it in there and be aware that we can use it if we need to. Frequently you will put more information into your diagram than you end up actually using. Well, maybe not frequently, but it's entirely possible anyway. So, let's show that these two triangles are congruent. Number one, we have a parallelogram. So, these two horizontal lines really are horizontal, and they're parallel. Well, what does that mean? Well, it means that this angle here and this angle over here are alternate interior angles. So they're congruent. Well, it turns out knowing these two sides are congruent is useful. We have the congruent angle here and congruent sides which form this angle, and that's our side angle side theorem, right? So this triangle must be congruent to this triangle. Now all we have to do is match up the corresponding parts, because corresponding parts of congruent triangles are congruent. Well, this side corresponds to this side corresponds to this side over here. Well, there's only one side left. This side corresponds to this side. And I made one mistake here. I hope only one. I shouldn't have used the same hash mark when I was showing that these two were congruent. It seems to imply that all four of these are congruent. They're not. This is congruent to this. And I drew a hash mark in here because I was about to show that these two sides are congruent. Well, what do we have here? This is 8, right? Didn't I say CF was 8? So this one must be 8. Where did we use the fact that BF was equal to 12? Or that DE was equal to 12? We didn't. We just used this part. This was the important part. The fact that their measure is equal, so they're congruent. For instance, if they just said BF is congruent to DE, that would have been enough to solve the problem. They just gave you the congruence in kind of a different way. So the actual measure of these two segments wasn't relevant. The fact that they were congruent, that's very relevant. Here's one that's kind of cool, because it's not that obvious that it would work. What we have here is just any old quadrilateral, not a parallelogram. And if we connect up the midpoints of each segment, forming the quadrilateral, we end up drawing a parallelogram. Whether we wanted to or not, we've got one. I redrew it down here fairly badly. I think maybe the midpoint should be over here a little bit so these would look more like real parallelograms. But that's okay. Don't worry about what it looks like. We're going to use our theorems. Remember, this is the midpoint of this side here, right? And this is the midpoint of this side here. What happens? Remember this, if we connect the two midpoints, I don't know if you remember back to when we were studying various components we could create out of a triangle. One of them was a midsegment, which connected the two midpoints of the sides of a triangle. And when we did that, we created a segment that was exactly half the size of the original, half the size of the opposite side. Or you could say the parallel side, but that's the fact that it's parallel is kind of irrelevant. We connect the midpoints because these are just two sides of a triangle now. We have a midsegment which is half of this. So first thing I should probably do is I don't like that. If we put some labels in here, label the vertices of the large quadrilateral A, B, C, and D, and then the inner midsegments, which they're not really midsegments because this whole thing isn't a triangle, it's a quadrilateral. But they become midsegments when we draw this diagonal. At least this one becomes a midsegment for this triangle. And we've showed that we didn't quite show, did we? We showed that this is half of this. What about this one over here? Well, this is a midsegment for this triangle. That means this midsegment must be half of this. So we've got that xy equals AC over 2. But that's also what WZ was. That was half of AC also. Well, that means xy equals WZ. So let's put our little hash marks in there. What do you think would happen if we draw in our diagonal the other way? Shoot, like that. What would we get? Exactly the same thing. This line would be the midpoint, or pardon me, the midsegment of the triangle formed when we used this diagonal. And this would be the other midsegment. They would both be half the size of this diagonal, meaning that they are both congruent. In other words, the argument I used for these two sides is identical to the one you'd use for these two sides. No difference at all. So it turns out that if you create a quadrilateral by connecting the midpoints of any other quadrilateral, you will end up producing a parallelogram. That seems kind of surprising to me. Actually, it's kind of cool too. If you ever want to make sure that you have a parallelogram, just draw any old quadrilateral, figure out what the midpoints are, and boom, you got it. May not be the easiest way to draw a quadrilateral, but you can be sure that you got it right. Well, this is funny. It looks kind of tough when you first glance at it. But having done the previous problem, this should actually look kind of simple to you. Because what do we have here? Like they said, they've drawn a couple of diagonals. Okay. This larger quadrilateral here, they tell you is a parallelogram. Okay. That means this side is congruent to this side. Well, we have a triangle here, and they're telling us that F and G connect the midpoints of these two sides, forming this triangle. Let's just forget about the fact that these are diagonals. Who cares? The point is, this forms a triangle. And this is a midsegment of that triangle, which means this is AB over 2. probably can't read that. I had to write it kind of small to fit it in there. But this mid-segment has to be half the length of this. Well, down here we have exactly the same thing. We've connected the two midpoints of these sides, which means this mid-segment is exactly half of this, or DC over 2. However, AB and DC are congruent. So, if, in other words, they're congruent, so AB equals DC. Now these two lengths are exactly half. This is half this one, this is half of this one. But the fact is, we can divide by 2 on both sides and still maintain the equality. We could call that our multiplication property of equality, or division by 2 property of equality, whichever way you'd like to look at it. But this side and this side are congruent, so let's draw that in. Well, that's a start, but now if we can show that this side and this side is congruent, are congruent, we're done. Because if both pairs of sides are congruent, we have a parallelogram. Well, the argument is identical for this triangle and this triangle. This is a mid-segment, so this is exactly half of this. This is a mid-segment, so it's half of this. And since this larger one is a parallelogram, AD and BC are equal, so AD over 2 equals BC over 2, and these two. So we have two pairs of congruent sides, so we must have a parallelogram. Well, like I said, this is really pretty easy. I was sure you wouldn't have any trouble, and I'm sure you didn't. The converse is, all you have to do is, when you remember the properties of a parallelogram, just remember that the converses all work. That makes it really easy. It doesn't always work out that way, but in this case it's pretty cool. So on tests, when you have to go back and forth, don't sweat it. You can, with confidence, go both directions with these parallelogram theorems. And that's kind of what made this section, I think, so easy, and why it's not really as long as most of them. Well, that's about it.